Hey everyone, I am Ms. Hu, your physics teacher. In this video, we'll be learning about impulse and impulsive force. What we'll be covering in this video are momentum, impulse, and impulsive force, as well as take a look at some worked examples and applications. Now, first things first, before we learn about impulse and impulsive force, we need to know what momentum is. Now, momentum is a physical quantity which can be calculated by taking mass times velocity. In terms of definition, momentum is one of those terms where the definitions can be taken based on the formula. That's why you can see over here, this is the definition of momentum. Momentum is the product of mass and velocity. It's quite simply the formula or the equation written out in words. The typical symbols used to simplify the equation is written this way. Momentum is usually P. Why P? I don't know, but let's just go with it. It's the lowercase p. Mass, of course, m, and v is velocity. So in symbol form, the equation for momentum is P equals mv. What is the unit for momentum? We can figure out the unit based on the equation. So based on this equation, we're going to use the SI units for those physical quantities. The SI unit for mass is kilogram, while the SI unit for velocity is meters per second. So when you multiply this together, as you can see, the unit for momentum is kilogram meters per second. Now, another unit that is accepted for momentum is Newton second, written as capital N, small letter s for short. So both of these are accepted units for momentum. So in case you're wondering, how is Newton second the SI unit for momentum? How is Newton second the same thing as kilogram meters per second? This can be proven when we look at impulse. We will learn about this in the next few slides coming up very shortly. A lot of my students have asked, what exactly is momentum? Okay, so momentum is mass times velocity. But what does this represent? Is it energy or is it some other kind of force? No, it's a whole different kind of physical quantity. It is not energy, not force, not anything else. It is a physical quantity all on its own, momentum. But if you look at the equation, you're wondering, okay, mass times velocity, what is it? A lot of students have a hard time understanding what it is. So don't try to understand what it is. What we need to understand about momentum is what it's used for. So when it comes to momentum, you will need to learn about momentum from two main concepts. We will need to learn it in terms of impulse and impulsive force, as well as the principle of conservation of momentum. So the reason why we learn momentum is because momentum is a key physical quantity when it comes to collisions. So when two or more objects collide, there will be a transfer of momentum, which we're going to look at in impulse and impulsive force, or there is a conservation of momentum, which we will look at in the principle of conservation of momentum. So momentum on its own doesn't really bear any logical meaning, but it's very useful when we are studying an overall pattern or an overall observation when it comes to collisions. Momentum is not only used in the calculations for collisions, but also explosions. Now, in this video, we're not going to cover everything with regards to momentum because it'll be a little bit too much. So I've split into two parts. So in this video, we're only going to be learning about impulse and impulsive force. If you would like to learn more about the principle of conservation of momentum, I have made a separate video on that, so do watch that video. For now, let's go into concept of impulse. The definition of impulse is the change of momentum. What does this mean? Usually something must happen to cause this sudden change of momentum. For example, if there's a collision, or if a force is suddenly applied that causes the velocity to change, causing the momentum to change. So when we say change of momentum, we're calculating the change of momentum for one object. That means the momentum of an object has changed because something has happened to it. An event has happened to this object, whether it's a collision or whether a force has been applied. Change of momentum means that there is an initial and final momentum where the values are different. Based on that, the formula for impulse would be final momentum minus initial momentum. Now remember that momentum is mass times velocity. And this is for the same object. So imagine that we have one object that has changed its momentum from one to another. There is an initial velocity and a final velocity causing an initial momentum and final momentum. If you can recall what you've learned in linear motion, there are different symbols used for the different velocities. U would be the initial velocity, while V is the final velocity. Therefore, this formula can be written in symbols using U and V. If mass is m, this means that the final momentum is mv, while the initial momentum is mu. So this is the formula for impulse. Now, impulsive force is rate of change of momentum, or in some syllabi, they write it out as change of momentum in a short period of time. Now, both of these are the same thing, but which definition you write depends on which syllabus that you are studying. So this definition is normally used in IGCSE, while this definition is normally used in SPM. So impulsive force is a rate of change of momentum. Now we know that the change of momentum is the final momentum minus the initial momentum. Rate means over time. So we're going to take this and divide this by time. So when we write it in symbol form, impulsive force is F, which is force. We know that final momentum is mv, and initial momentum is mu, and time can be written as t. So this would be the formula for impulsive force. Now, one thing that you must be aware of is that when we substitute the value of time in this equation, the time that's being referred to here is specifically impact time. So impact time here means the time of collision. So before, obviously, it's not impacted yet. So impact time is the time when both objects are in contact with each other during the impact. Then if they separate, then the time has stopped. So depending on the collisions, impact time can be known in many different terms. For example, it could be called stopping time, contact time, even landing time is possible. Just be aware that the time in this formula, specifically the time in which both objects are in contact with each other during the collision only. Now let's put that together side by side to compare. I'm going to use the symbols here because they'll be easier for us to compare straight away. If I were to write it with a lot of words, it's just going to muddle up the entire slides. So we know that impulse is mv minus mu, whereas impulsive force is F equals mv minus mu over t. Now if we look at this side by side, you can see that they're actually related because mv minus mu, which is the top part of the fraction here, is quite simply impulse. If we were to rewrite this formula, bringing t up to the same side as F, I'm going to write it over here, you'll find that Ft equals mv minus mu. Now, yes, so now you can see that on the right side, it's the same thing. The left side is Ft. What does this tell us? This tells us that impulse can also be calculated as impulsive force times time, Ft. So impulse is not only calculated as mv minus mu, but can also be calculated as Ft, force times time. Now because impulse is mv minus mu as well as equal to Ft, you should be able to see that another way to calculate the impulsive force is to take force, which I'll write here as F, as equal to impulse divided by time. Because impulse is equal to mv minus mu, Or we can also derive it from this formula by taking time and shifting it over to the other side under the fraction of impulse. And that's how you get F equals impulse over time. Based on this summary sheet, you can now see that there are two formulas to calculate each, impulse and impulsive force. So impulse, you can calculate it as a change of momentum, mv minus mu, or you can take it as the impulsive force times time. For impulsive force, you can calculate it as a change of momentum over time or as impulse over time. Now, one more thing I'd like to show you is the relationship between this impulsive formula and the general formula for force, which you should already know by now. I'm going to write it over here at the side. I know it's not very much space, but it's just to show you that relationship. You see, if you can recall what you've learned about linear motion, you know that A is V minus U over T. We also know, based on Newton's second law of motion, F equals ma. Now, can you see the relationship between F equals ma and this impulsive force formula? If you take this formula and take m out as the factor, you get V minus U divided by T. Can you see that this impulsive force formula is actually the same as F equals ma? So in case you can't remember the impulsive force formula, but you do know that F equals ma, you can just take the acceleration equation, open that up, and you can calculate impulsive force from there. So yes, impulsive force is just quite simply force written with the formula expanded. Now let's talk about the units. We'll start off with impulsive force first because that's a lot easier to understand. As we know, impulsive force is a type of force. Therefore, it shares the same unit as force. The SI unit for force is Newton, which means that the SI unit for impulsive force is also Newton. So I'm going to write that underneath here, that the unit is Newton. For impulse, let's look at the two formula. The first formula shows us that impulse is a change of momentum. The unit for momentum, as we know from mass times velocity, is kilogram meters per second. Because it's change of momentum, kilogram meters per second minus kilogram meters per second, that's why the unit for impulse is also kilogram meters per second. Another possible unit is based on this formula of force times time. As we know, force is Newton, while time is second. And as you can see, this formula shows us that another derived unit is Newton times second, giving us Newton second. And that's why impulse has two possible units, which are kilogram meters per second as well as Newton second. Now, if you can recall what I mentioned when I introduced momentum at the beginning of this video, momentum has two possible units, kilogram meters per second and Newton second. So let's just go back to that slide. The reason why momentum has two units, which are kilogram meters per second and Newton second, is because of impulse. The unit for Newton second was actually derived from the impulse formula. And based on these two formulas, this shows us that kilogram meters per second is equivalent to Newton second. So you can either write the unit as kilogram meters per second or Newton second. They both have the same value. Because kilogram meters per second equal to Newton second, that's why for momentum, you can also write the value of momentum as kilogram meters per second or Newton second, because these two units have the same value. Now let's look at some worked examples so that we can understand better about momentum, impulse, and impulsive force. So one of the common examples where we can see impulse and impulsive force in real life is when we jump and we land. So I want you to think about it. Let's say this is you and you're jumping to show off your parkour skills. Woohoo! Now, there are many ways in which we can land. Which landing is the safest method? Would it be to land with straight legs, bent knees, or maybe you want to land and roll? Even if you don't do that wild sport, you should know by now, landing with straight legs is obviously a really bad idea. And that's because when you land, the force will go into the joints of your body. So you could potentially even break a bone. So landing with bent knees is a lot safer. And the safest is if you know how to land and roll, then that would be the one that gives you the least injury. So yes, this is all about the impulsive force. Why is it though that landing with bent knees is safer than landing with straight legs, and landing and rolling is even safer? It's everything to do with the impact time. So to help you visualize this, I am going to write out the formula for impulsive force, and in this case we're just going to use the formula to make it easier for us to quickly take a look at the comparisons. So we know the formula for impulsive force is F equals mv minus mu over t. If I take m out as the factor, leaving v minus u over t, we can now take a quick look at this example and see how that applies in this formula. The m in this case is the mass of the person that is going to land. Obviously, in all these cases, the mass of the person would be the same. So when we compare these different situations, mass is not a consideration. What about v and u? V and u would also be the same. Now, just to point out to you, v and u refers to the final and initial velocity before and after reaching the ground. A lot of students tend to get very confused. They thought that the initial and final velocity and even the time in question is during the motion where this person, if that's you, then that's you, this person is falling through the air. Now, this is the falling motion, and yes, this motion does have initial and final velocities, but this is not the motion which we are considering when we want to take the values of u, v, and t. The values for u, v, t which we want to consider would be when we are reaching the ground. So the initial velocity of u in this case is the velocity of the person just before hitting the ground. Why do we say just before hitting the ground? Because once the person has reached the ground, the person has come to a stop. So that velocity is 0. That's not the initial velocity. The reason why the person comes to a stop is because of the impact against the ground. So the final velocity would be 0 because the ground has made the person come to a stop. So I'm going to write that over here as v equals to 0. So u is the velocity just before striking the ground. Because as you should know by now, when it comes to objects that are falling, as we fall through air, we increase in velocity. So just before we hit the ground, that would be the highest velocity of that motion. So just before striking the ground is that split second just before we come to a stop. Then when we reach the ground, we stop. So u is the velocity just before reaching the ground. Now, whether we're landing with straight legs, bent knees, or we land and roll, the velocity just before reaching the ground would be exactly the same. Because if you can remember what you've learned about objects that fall with gravitational acceleration, the increase in velocity depends on the gravitational acceleration, and the value of the velocity just before reaching the ground will depend on the height that we jump off. The greater the height, the greater the velocity just before reaching the ground. The mass of the person does not matter. So in all these cases, m, v, and u would be the same. What is different is the value of t, which is the impact time. So the reason why it's so dangerous and so bad to land with straight legs is because the impact time is very, very short. Because when you land, you just come to an immediate stop. The impact time is very short. Now, when we land with bent knees, we prolong the time it takes for us to come to a stop. Because as you land, you're still moving, and only when you, okay, I'm done, that would be the end of how we calculate impact time. So that's why it's safer to land with bent knees. If we land and roll, that prolongs the landing time even more because the time only stops when the person has come to a stop. So if you're rolling, the time still counts. So the impact time is how much time it takes for the person to land and change the velocity from this value of u to this value of v. Now let's do a worked example based on this situation with numbers so that we can see the comparison between these different landing styles and how the impact time affects the impulsive force. A person with mass 55 kg jumps off a ledge. The velocity just before reaching the ground is 6.2 meters per second. A. Calculate the impulse upon hitting the ground. So as we've just learned, impulse is the change of momentum. Impulse is calculated as the final momentum minus the initial momentum. So when the person hits the ground, the final velocity will be 0 because this person comes to a stop. So that means it's 55 times 0. The initial momentum is calculated as 55 times 6.2, which is the velocity just before hitting the ground. So this would give us negative 341 Newton second. So those of you who are taking IGCSE, you may not need to write the negative symbol because in IG they do allow you to write just the magnitude, so you can leave it as positive 341 Newton second. If you are taking SPM, you do need to write the negative value because you have to show clearly that the final momentum is 0. So that's why you end up with a negative value. For now, I'm going to leave this as negative because the negative value is the actual value in this case. Let's calculate the impulsive force. So as we know, impulsive force is impulse divided by time. So all we need to do to calculate the answers for B1, 2, and 3 is to take this value of impulse divided by the respective impact times. So I'm going to write that over here. So B1, let's get straight to it. F equals to negative 341 divided by 0.5, which gives us negative 682 Newton. So that's quite a lot. For question B2, it would be negative 341 divided by the impact time of 2.0. And that gives us a value of negative 170.5 Newton. If you're writing this in IGCSE, of course, you have to round it to 2 to 3s in figures. You can just write it as negative 171 Newton. For question 3, it would be negative 341 divided by 10, which gives us negative 34.1 Newton. So as you can see, the greater the impact time, the lower the value of the impulsive force acting on our bodies. That's why the longer we can prolong the impact time, the lesser the impulsive force will be acting on us. Now, let's take a look at this example. So if we were to push a watermelon and push an egg off the table, what's going to happen? Now, if they're both going to hit the ground, obviously they're going to crack. So just to let you know, it doesn't matter what the mass of the object is. So you could have a huge heavy watermelon like this and a much smaller lighter egg. If they both fall off the same height, they will both reach the ground at the same time. So this is what you should have already learned under the concept of free fall or falling with gravitational acceleration. The mass doesn't influence the velocity it gains. It's the height of the release which will influence the velocity only. To understand why, please watch my video on how mass does not affect gravitational acceleration. So for this example, let's not waste a watermelon. We'll talk about breaking an egg instead. So if we drop 2 identical eggs off the side of a table, if dropped on a hard surface, the egg would crack. But if you drop it onto a soft surface like a mattress, the egg would not crack. So the reason for that is also the impact time. On a hard surface, the impact time is much shorter because it comes to a stop very fast. Whereas on a soft surface, the soft surface will absorb that impact, prolonging the impact time. So again, let's look at an example with numbers so that we can compare that impact time against the impulsive force. 2 identical eggs with mass 60 grams each fall off a table. Both reach the ground at a speed of 5 meters per second. A. Calculate the impulse of the eggs. So it doesn't matter whether it hits the ground or it hits the sponge. They would both have the same impulse because they both reach the ground at the same speed. So impulse is a change of momentum. We'll take it as mv minus mu. The mass is 60 grams. I'm going to convert it to kilograms because it's much better to write it in SI units. Now to make it easier, I'm just going to factorize m because then we don't have to substitute so many times. We have 0.06 kilograms for mass, and then v of course is 0 because it comes to a stop. That's the final velocity. So the initial velocity would be the speed at which it reaches the ground. That's 5. And this gives us a value of negative 0.3 Newton second. So once we have the impulse, it's very easy to calculate impulsive force now because all we need to do is take the impulse divided by time. So for the egg that lands on the floor at an impact time of 0.1 second, the force is the impulse of 0.3 divided by the time of impact of 0.1, giving us a value of negative 3 Newton. For question C, the impact time is 2 seconds. So we'll take negative 0.3 divided by 2, and that gives us negative 0.15 Newton. So again, you can see from here, the greater the impact time, the lower the impulsive force. Let's take a look at one more example. A 56-gram tennis ball hits a wall and rebounds at the same speed. So if the initial speed in which it makes contact is 40 meters per second, calculate its impulse. Now it rebounds at the same speed, which means that the final velocity is also 40 meters per second. So to calculate the impulse, all we need to do is take the change of momentum. Now the change of momentum is the final momentum minus the initial momentum. I'm going to take m out as a factor because it just makes it easier for substitution. Now they've given us the mass here as 56 grams. Again, I would prefer to write it in kilograms, so I'm going to convert the mass to kilograms. That's why I'm writing the value here as 0.056, which is in kilograms. Now you cannot put 40 minus 40, you're like, oh, that's 0, impulse is 0. Now this is obviously wrong. You must remember that the question told us that it rebounds, and as I've drawn arrows over here, the ball will be moving in opposite directions. That means one of it would be in negative. You can take the final velocity as negative or the initial velocity as negative. It is totally up to you. The question didn't tell us whether it's moving to the right or moving to the left initially, and it honestly doesn't matter in this case. Just to go against the grain a little bit, let's say the initial velocity, we take it as negative this time, and the rebound, we take it as positive. It's okay for us to do this. So this gives us 40 minus negative 40, which would give us 0.056 times 80. So one advantage of doing this is that then our final answer would be a positive value, and this would give us 4.48 Newton second. So the impulsive force is the value of the impulse calculated divided by the time, which is 0.3 seconds. This would give us a value of 1.49 Newton. And that's how you solve this kind of question. What if you had put negative 40 minus 40, then you get negative 80. You would still get the same magnitude, just that's in negative value. It will actually still be accepted because in this question, they never specified where's positive and negative in the first place. The important thing here is that we know how to get the magnitude of the impulse and thereafter the impulsive force. Now, let's take a look at a few applications. So let's think, why must a mattress be used in the landing area of a high jump? Obviously, if we don't have the mattress, the high jumper is going to suffer severe injuries when he hits the ground, right? But remember that when we want to write the answer out, we must write it using the correct physics keywords and explain the correct physics concepts appropriately. So the correct way to say this is that a mattress is used to increase the landing time in order to decrease the impulsive force. So whenever we discuss the applications, always talk about how the time affects the impulsive force. Here's another example. Why can we only crack an egg open on a hard surface? Now this is obviously opposite to using the mattress for a high jumper. The hard surface will decrease the impact time, which will increase the impulsive force. So that's how we can write our answer out for this kind of question. So depending on what the question is asking, look at whether you need to increase or decrease impulsive force. Then you describe how the impact type should be changed to get that value of the impulsive force needed. And in terms of everyday safety, a very common application of our understanding of impulse and impulsive force is in terms of car safety. So when we look at all the safety features added to a car, like the front crumple zone, the anti-lock braking system, side impact bar, safety belts, rear crumple zone, passenger safety cell, safety glass and airbags, these are all safety features that have been added to a car in order to protect the drivers and the passengers. Many of the safety features are added because they can prolong the stopping time in order to decrease the impulsive force acting on the people inside the car. Now, for some exam syllabi, they do go through the safety features of a car quite extensively, but I will not cover that in this video because it can be quite lengthy. So instead, I will explain those in another video. For now, that is it for this lesson. So if you found this video to be educational and helpful, please click like and do subscribe for more free physics lessons from your physics teacher, Ms. Ho. Do check out my YouTube channel for videos on other topics which you might find very helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page, that's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Happy studying!